For the first time, astronomers are not just imaging a black hole, they are attempting to record one in motion, capturing how matter behaves as it swirls, heats up, and disappears at the edge of gravity itself. In 2019, we got a single image that changed black hole science, a bright ring around a dark center. Now, astronomers are trying to do something even harder, turning that single moment into a moving sequence. Actual snapshots of a black hole's surroundings, taken repeatedly and stitched into the first movie of a black hole in action. The target is the same one that made headlines in 2019, the supermassive black hole in Messier 87. So what does filming a black hole really mean? And why does this matter if we already have a picture? In 2019, the world saw something unprecedented, the first image of a black hole. It showed a glowing ring of light surrounding a dark center, the shadow of a supermassive black hole at the heart of the galaxy M87. That image confirmed decades of theoretical predictions. It demonstrated that Einstein's equations worked even under the most extreme conditions known. But the image was static. Black holes are not frozen objects. The gas around them moves at enormous speeds. Magnetic fields twist. Matter heats, cools, and rearranges itself constantly. Jets form, flicker, and propagate across thousands of light years. Astronomers have long known this was happening. They just couldn't see it unfold. M87 is a massive elliptical galaxy located about 55 million light-years from Earth, sitting near the center of the Virgo Cluster. It contains trillions of stars and an unusually large population of globular clusters. But its most remarkable feature lies at its center. The black hole in M87 has a mass of roughly 6 billion times that of the Sun. That makes it one of the most massive known black holes in the nearby universe. More importantly, it is active. Not all galaxies host active black holes. In fact, only a small fraction do at any given time. Most supermassive black holes are relatively quiet, slowly consuming whatever matter happens to drift close. M87's black hole is different. It is surrounded by a bright accretion disk, a rotating structure of gas and plasma heated to extreme temperatures as it spirals inward. And from this region, it launches a relativistic jet, a narrow beam of particles accelerated to nearly the speed of light, extending thousands of light years into intergalactic space. This jet has been observed for over a century. Long before astronomers knew black holes existed, they noticed a strange streak of light emerging from M87's core. Today, that jet is considered one of the clearest examples of black hole-driven activity in the universe. Black holes are often described as cosmic vacuum cleaners, objects that swallow everything around them. Black holes do not wander the universe consuming stars at random. Their gravity, at a distance, behaves like that of any other object with the same mass. What makes them extraordinary is what happens very close in, near the event horizon. In active galaxies like M87, black holes act less like destroyers and more like engines. As gas falls inward, it forms a disk. Friction and magnetic turbulence heat this material to billions of degrees. Some of it crosses the event horizon and disappears. Some of it is redirected outward along magnetic field lines, forming jets that carry enormous amounts of energy far from the galaxy's center. These jets can suppress star formation, heat surrounding gas, and reshape entire galaxies over billions of years. Understanding how this process works is one of the central questions of modern astrophysics. To film a black hole, astronomers needed something unprecedented, a telescope with resolution high enough to see an object roughly the size of our solar system from tens of millions of light years away. Therefore, scientists built a global instrument. The Event Horizon Telescope is a network of radio observatories spread across the Earth from Antarctica to Hawaii, from Europe to South America. By synchronizing these telescopes using atomic clocks and combining their signals, astronomers effectively create a telescope the size of the planet. This technique, called Very Long Baseline Interferometry, allows the EHT to achieve angular resolution far beyond what any individual dish could manage. In 2017, this system was used to collect the data that eventually became the first image of M87's black hole. Since then, the array has grown, more telescopes have joined, sensitivity has improved, data processing methods have advanced, and now, instead of producing a single image every few years, the EHT can generate snapshots every few days. A black hole itself does not emit light. What the EHT sees is the glow of superheated gas orbiting just outside the event horizon. In M87, this gas completes an orbit on timescales of days to weeks slow enough relative to smaller black holes. The changes can be tracked over time. By collecting repeated observations and aligning them carefully, astronomers hope to assemble the first time-resolved sequence of a black hole environment. Not a video in the traditional sense, but a scientifically meaningful record of motion, how bright regions shift, how the disk structure changes, and how magnetic features evolve. This will allow researchers to test models that, until now, existed only in computer simulations. One major goal of the campaign is to measure the spin of the black hole. Spin is a crucial property. It carries information about how the black hole formed and evolved. A rapidly spinning black hole likely grew through steady accretion over long periods. A slower spinning one may have grown through mergers with other black holes. Spin also affects how efficiently energy can be extracted from the black hole's surroundings, particularly in the formation of jets. By watching how material moves near the event horizon, astronomers can infer how fast the black hole is rotating and how its angular momentum influences the surrounding spacetime. Despite decades of study, the precise mechanism that launches black hole jets remains uncertain. Scientists know that strong magnetic fields are involved. They know the jets originate near the inner edge of the accretion disk. They know black hole rotation likely plays a role. What they don't fully understand is how these ingredients combine to produce a narrow, stable, long-lived beam of particles moving at nearly the speed of light. M87 is an ideal laboratory for studying this process because its jet is both powerful and relatively close. By correlating changes in the accretion disk with activity in the jet, the EHT data may reveal how energy and angular momentum are transferred from the black hole system into its surroundings. Observing a black hole is not just an astronomical challenge, it is a logistical one. The EHT generates enormous volumes of data, far too much to send over the internet from remote observatories. Instead, data is stored on physical hard drives. In Antarctica, where one of the key telescopes is located, those drives must wait months until the end of winter before they can be transported out. Only after all the data are gathered in central processing facilities can the work of calibration, correlation, and image reconstruction begin. What the public eventually sees represents years of effort by hundreds of scientists, engineers, and technicians across the globe. For decades, black hole physics has relied on indirect measurements, spectra, light curves, theoretical models. Those tools remain essential. But direct, time-resolved imaging adds an entirely new dimension. It allows scientists to see whether their equations describe reality as it unfolds. And it helps place black holes in their proper role, not as exotic oddities, but as central players in the evolution of galaxies and the universe itself. No observation will ever show what lies inside a black hole. The event horizon marks a boundary beyond which information cannot escape. But what happens just outside that boundary is among the most extreme physics accessible to observation. In that region, gravity warps space and time. Matter behaves in unfamiliar ways. Energy flows along paths shaped by geometry itself. By filming a black hole in action, astronomers are not peering into the unknown. They are watching the known laws of physics push to their limits. If you genuinely enjoy exploring the universe and its mysteries, consider subscribing. It helps us keep going. If we can now watch a black hole change in real time, what do you think we're most likely to learn first? How black holes grow, how they launch jets, or how they shape entire galaxies? Let us know in the comments.